All right, so we ended, roughly speaking, right here last time. I am so thankful I have this all prepped up for you guys because we're just going to scroll through it, more or less. So here's the idea. There are roughly speaking, three categories that you can divide a Hilbert plane into. So first assumption is we must have a Hilbert plane. So no models of geometry that are funky like our taxicab model that turned out not to be a Hilbert plane. We have to properly be a Hilbert plane. Once we're a Hilbert plane, we look to see, does Playfair's axiom hold or not? If Playfair's axiom holds, we're going to be in the semi-Euclidean situation. The sum of all the interior angles will end up to be 180 degrees. And I'm going to just tell you, this is called the defect. The defect would be 0. It's 180 degrees minus whatever your angle sum is. That's all the defect is. You don't need to know about it for what we need. Today's our last day of class. In terms of the non-Euclidean geometries, these are the geometries where Playfair's axiom doesn't hold. And it turns out there's two cases. One is when you add up all of your angles, that sum is bigger than 180, and the other is that sum is less than 180. Well, it turns out if the sum is bigger than 180, and you can do the algebra and you'll get the arithmetic and you'll get back the defect is positive or negative. And again, we're not going to care about that for right now. But if the sum of angles is bigger than 180, this is what's known as semi-elliptic or an elliptic plane or an elliptic geometry. And that happens when you're on a sphere, so on the outside here. And notice here, if we actually pretended this was an equilateral triangle, my horrible little freehand drawing here, what we would see is equilateral means all these angles are congruent, which means they all have the same degrees. Well, if the sum is bigger than 180, and you have 3 times the unknown thing, divide by 3, that tells you that the measure of each angle is going to be greater than 60 degrees. And if you ever try to measure the degree of some angle on a sphere, first of all, it's difficult because it's a sphere. But what you'll notice is if you actually did have an equilateral triangle here, it would come up to be larger than 60 degrees. And just as a heads up in terms of lines and points. Points, same as always, but in terms of lines, how to think about them is at each point putting in something like a push pin. So maybe you have something like a styrofoam ball. You put in a push pin at each of your points, then you take a string, you wrap it around the pin on one side, you wrap it around the pin on the other side and make it really tight. Where that line settles on the actual sphere, that's your line of your geometry. Please note, just by convention and because we're writing here on a flat piece of paper, what we do is we bow these sides out to indicate that we're actually going around a sphere. It's kind of like making it perspective drawing. The exact opposite is true for the other type of non-Euclidean geometry. This guy is called a hyperbolic plane or a hyperbolic geometry, or technically semi-hyperbolic, semi because we're not talking about the circle axiom, or E. Here, the sum of the angles is less than 180, and in terms of how it looks, you look at this guy here. So notice how this is not the technical words, but it's kind of like concave in, except it's in 3D. So the plane, the Hilbert plane, is the surface area of this shape right here. And so notice here, these lines are trying to indicate that it's all curving in. It's like, as somebody said previously, it's like the inside of a sphere, although that's not the best way to picture it. Okay? But that's sort of the curvature. In this case, if we make an equilateral triangle, again, assuming equilateral, you'll have all the sides are congruent, all the angles are congruent. We know that from being in a Hilbert plane. So here, if we say all of our angles are congruent, we'll divide by 3 on both sides, and we'll solve for the measure of each of the angles now has to be less than 60 degrees. And by convention, what people do here is they say, hey, I'm going to have all of my sides sort of bow in. I totally think of it as like sucking. We've sucked all the innards out of our triangle. I realize that might be not the way you want to think about it, but that's totally the way that I think about this one, or this one is like pushing air in or you're blowing it up. All right, now here's a new thing. New things that we want to talk about is something called a Subsidiary Quadrilateral. Now, quadrilateral, we know what that is. It's a polygon of 4 sides, or a 4-sided figure. And here's how it's defined. You're in a Hilbert plane. You're going to be given some base AB, and we're going to have 2 other sides, AC and BD, are both going to be congruent to each other and perpendicular to your base AB. And then once you have your points C and D from these 2 sides, you're just going to find the line in the geometry and connect them. Now, if we're in a Euclidean plane, or Playfair's axiom holds, what happens? Well, if you have two right angles here and two sides that are congruent, this is something we've done all the time, we're automatically going to get a rectangle here. Okay? This line will be parallel to that line. You'll have two right angles, one at angle C, one at angle D. Now, if you're in an elliptic plane or semi-elliptic plane, you'll still get the base, you'll still get the sides are congruent, you'll still get the right angles. But when you throw this onto the sphere, on the sphere, it'll actually look like these two sides, A, C, and B, D, are sort of moving away from each other the further they're getting from the base. Remember, parallel line or Playfair's axiom doesn't hold here, so parallel lines can be weird. Now, what do we do next? When we join these 2 points, if they look like they're getting farther away up here, or even if they don't really look like they're getting farther away up here, you watch out for what's going on. This guy here is sort of bowing out to indicate perspective, and these 2 angles at C and D are going to turn out to be congruent, but they're going to turn out to be obtuse angles. That's bigger than 90 degrees. So, weird, but true. Now the last guy here, suppose we'd had this Sagittarii quadrilateral in the hyperbolic plane. This is the plane that's on this figure here that's sort of bowing in the wrong way you might not want it to bow. But here in terms of perspective, it looks like the top sort of fell. Its balloon let out all of its air type thing. So here again we have the base, we have the sides that are perpendicular to the base, the sides are congruent to each other. But in this case it's going to turn out the 2 angles C and D, they're still going to be congruent angles, but they're going to be acute angles. So that's what a Sagittarii quadrilateral is. First example for us is using a Sagittarii quadrilateral. So this is going to be proposition 34.1, and we're in a Hilbert plane, and we're going to start off with a Sagittarii quadrilateral. And I did the same definition we just did for up there, so it's going to look like one of these 3 pictures. And I'm going to go ahead and pick on the elliptic plane right here, so our picture is going to look exactly like this guy. So what we're going to show is we're going to prove that angles C and D are congruent to each other. While they will turn out to be obtuse angles, so bigger than 90 degrees, that's not going to be part of this proof. And we're actually not going to prove that, I'm just telling you that. And then the last thing is we're going to deal with this thing called a midline. And a midline is where you take the midpoints of AB, your base, and CD, your top, and join them together. And this claim here, or really the second claim in this proposition, that this midline is perpendicular to AB as well as CD. In a rectangle, what would you get? You get a line that's parallel to the sides. Okay. We're not assuming Playfair's axiom holds, so no guarantees about that in the other 2 guys. So this guy was drawn ahead of time. It actually came from last semester. Again, I can't draw anything with a stylus today until I get new batteries. So you're going to see some things that normally we wouldn't mark up till we're further on out, so bear with me on that. So here's the original picture with tons of extra markings, okay? But it does give us the outline of what we're going to do. So here's what we're going to do. All that we're given is this original Sagittarii quadrilateral, the outermost bits. We're going to put in the midline, we're going to put in this EF line, we're going to call that our midline. We're then going to include 2 extra lines, A to F and B to F. Note, when in doubt, form triangles. We just formed 4 triangles right here. Okay. We needed the midline because it was part of this statement, and then we formed extra triangles. If we didn't need the midline, maybe we would have formed triangles in some other way. Okay. Now, what are we going to do? We're going to try to show that the inner 2 triangles are congruent to each other. Then we're going to try to show that the outer 2 triangles are congruent to each other. And if we can show the outer 2 triangles are congruent to each other, we will totally get right here that angle C and angle D are congruent, which is the main thing that we want. And it turns out with a little bit of fleshing out, we'll get the second step as well. Okay. So first thing is just going to be some givens. We are given that this guy is a Sagittarii quadrilateral. It means you've got perpendicular lines or right angles at A and at B. It also means A, C, and B, D are congruent to each other. So that was just given. Second thing we're going to do is we're going to go ahead and form this midline. So to do that, it's a 3-step process. Technically, you could do it in 2 steps. The first thing is we find the midpoint of AB, so that's point E right here. And then we're going to find the line that's perpendicular to AB through E. Note, if you do perpendicular bisector, you've got it in 1 step. Okay. Now, this line right here, we're going to extend or take the full line in the Hilbert plane. So what we want to know is, does this point F exist? Step 4 here says on our line that we formed, that orange line, point F totally exists because our line that we called L originally and CD will intersect due to plane separation. There's multiple ways you can reason this out, but roughly speaking, you've got points on either side of your line L. If A and B are on either side of this line because you know E exists, B and D are on the same side of the line, A and C are on the same side of the line, so C and D have to be on opposite sides, which means F has to exist. So technically, you could have broken that up into like 3 steps with transitivity. I didn't. Now, once we've established that we've got this line, the new things we have are the fact that E here is perpendicular to AB by way of the construction. Now, second thing we want to do is we want to show that these two innermost triangles are congruent to each other, and let's think about what we just found. E is the midpoint, so that means AE is congruent to BE. We also know that the two angles at point E are right angles, which means they have to be congruent to each other. And the two inner triangles share the line EF, and if a shared line is always congruent to itself. So let's write that down. One more. The only thing that I missed here was actually drawing in these lines AF. These other 3 are exactly what we just said. Now, once you have the 2 pairs of sides that are congruent and a shared pair, those 1 pair of angles that are congruent, we totally can pull out any guesses what we're going to use to show that our innermost triangles are congruent to each other? Anybody spot what we're building up to? In other words, we're going to use blank to show the 2 triangles are congruent. Almost. It is one of the triangle congruence theorems, so your options are, that's not a triangle congruence theorem. Your options are side, 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 angle, side, angle, side, angle, 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 side, or right angle, side, side. There's 5 of them. Technically speaking, we have a right angle, but we can't use right angle, side, side because it requires the use of the hypotenuse that we don't know yet. Angle, side, angle, we don't have the second angles are congruent, even though they're all marked up here, we've marked a little bit too much. Side, side, side doesn't work because we have 2 pairs of sides, that's cool, but we still don't have that 3rd pair of sides, ugh. So the only thing that's left is side, angle, side, which, yay, side, angle, side. The only thing I have to check is the angles between the 2 pairs of sides. Bam. And if you want to be super duper fancy, you could say our triangle congruence theorem C6. But optional if you want to be that fancy. Now, this is why I said the picture's a little bit of a misnomer, because we're not building it as we go along. So we've got these bits down. As soon as you get the 2 triangles, those 2 innermost triangles are congruent, automatically by corresponding parts, you get the remaining 3 pieces and parts of your 2 triangles congruent. Namely, you'll get the hypotenuse, AF and BF are congruent. That picks up those guys that are already marked. You get the angle at A, that lower angle, and the angle at B, that lower angle, are congruent. And the 2 inside angles at F are also congruent. In other words, all the information inside of the lower 2 triangles right here is totally accurate right now. Here's the part that's not accurate. All of these markings on angles out here, we haven't shown them yet. Although we do still have BD is congruent to AC. So I am going to claim the next thing that we want to focus in on are these outer 2 triangles. So ACF and BDF. We want to show that those 2 guys are congruent. But what do we know so far? Well, we know AC is congruent to BD, because that was given. We just found that AF is congruent to BF. Awesome. We know nothing about the CF or DF, so we've got to be able to find a triangle congruence theorem that deals with 2 sides. There's only 2 options. Right angle side, side, and side angle, side. Now, unfortunately, you don't know that angle C and angle D are right angles. You know for sure angle A and angle B down here, the upper ones are not right angles because they're part of a bigger right angle. And you have no idea what's going on over here at F. Probably not going to be right angles because, well, it's a single line and you already have 2 angles being pulled out of it. So that eliminates us down to side angle side. Well, that's okay. We've got two sides that are congruent. We can know something about this side here at this angle here at A, the upper one, and the upper angle at B. So what do we know? The full angle at A is a right angle. The full angle at B is a right angle. So those two guys are congruent. If you have two right angles and you subtract off two congruent angles here, the lower angle at A and the lower angle at B, you should what? Well, pair of congruent angles, subtract from both of them a second pair of congruent angles. Well, the subtraction should still be congruent, which is exactly what this step 11 says. Hey, the upper angle at CAF and DBF are supposed to be congruent. And notice that was the one thing we didn't have to apply side, angle, side. So we apply side, angle, side, and that tells us that those upper angles, not upper angles, those upper triangles are totally going to be congruent to each other. Bam, basically done. Now it's just writing up the answer. So as soon as you have that these two upper triangles are congruent to each other, all the missing pieces and parts are also going to be congruent. So we get immediately that angle C and angle D are congruent, which was the big thing we wanted to prove in this proposition. So bam, we're done at that point. Now, there was one extra thing that we were supposed to prove, and we're supposed to prove that we had a midline and it needed to be perpendicular to the base and to the top. Well, we made a line that was perpendicular to the base through the midpoint. So in order to show that this is a midline, we need F to be a midpoint, and we need EF to be perpendicular to CD. And it turns out we're basically there. We just have to write it up. The corresponding parts will also give you, as we just barely see these guys, corresponding parts are going to give you not just that angle C and D are congruent, it'll also give you that CF and DF are congruent. Well, that means F is the midpoint. We needed that. And it tells us the angle at CFA and DFB are congruent, which is, again, a really good thing. So we just said F is a midpoint of CD. There should be a line on top of that. So this tells us that EF really is the midline. We already know EF is perpendicular to AB, so the only thing left to do is EF is perpendicular to CD. Well, if we look at CFE and DFE, CFE, DFE, we added two congruent pairs of angles together. That means what? That means these two new angles on either side of the orange line have to be congruent to each other. And I'm going to claim that those two angles are already supplementary to each other. Why? Because CD was a line and you have another line that comes and sits on it. Definition of supplementary. Well, if you have a pair of angles that are both supplementary and congruent, anybody remember what that means by definition? And it's literally the definition of a type of angle. Supplementary and congruent. Anybody recall? That would be the definition of a right angle. And as soon as you have the definition of a right angle, if you recall, both in classical geometry and now in Hilbert geometry, when we define right angles and perpendicular lines, it's all the same definition, just two different ways of phrasing the same thing, whether you're referring to the angles or whether you're referring to the lines. So as soon as you get that you have right angles, bam, immediately we get that the two lines, the midline and the top CD are perpendicular, and that gives you the last thing that you wanted here. Although, to be fair, the thing that was actually the most interesting about this whole question was the fact that angle C and D were congruent, and we had that a while back. So that right there is why I was telling you earlier, always up here at the top, CD, 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 in any of the three cases, we're going to be congruent to each other, just sometimes acute, sometimes obtuse, and sometimes right. It was using that fact. And that's it for that example. Notice, when we work through this, there was nothing at all that corresponded specifically to whether we were in a not a Hilbert plane, we were definitely in a Hilbert plane, whether we were in a semi-Euclidean plane, whether we were in a semi-elliptic plane, whether we were in a semi-hyperbolic plane. This just worked because we were in a Hilbert plane. So regardless of what was going on with Playfair's axiom or wasn't, this guy still works. Okay? Notice this is also something we've totally done before. We could have actually done this exact problem or this question or this proof back when we were in Chapter 2 when we were still dealing with just only Hilbert planes before we gotten into anything more advanced. Okay? So there's nothing specific to the non-Euclidean geometries here, but it still totally works with all of them as well, because as long as you're a Hilbert plane, this guy will work. The new thing really was a definition of a Sagittary quadrilateral. So these guys here are two interesting propositions. I'll highlight proposition 34.2, but I'll let you guys read over these your own in your book because we're not going to get into them this semester. So proposition 34.2 says you've got some quadrilateral A, B, C, D, so up here to D. You've got right angles at A and B, but AC and BD are not congruent to each other. Okay? Then in this case, it turns out the angle C here is going to be larger than the angle at D as long as AC is the shorter of the two sides. Please note here, you can actually prove this by way of forming a Sagittary quadrilateral right here and then using that extra little triangle that got formed on top. But it's fascinating. The longer side is the side that has the smaller angle. And this one here, both of these two pictures are drawn in a hyperbolic geometry. How would I know that? Because these lines look like they're sort of dipping or they're sagging or they're being sucked towards the bottom down there. Okay. And that's perspective-wise what we do when we're dealing with hyperbolic planes. All right, let's actually see the second example that I wanted to talk about tonight, and it is this guy. We've actually done this exact example back when we were in classical geometry, and in classical geometry is not exactly the same, but it's similar to being in a Hilbert plane. Not a Hilbert plane, Euclidean plane. So here, you're in some Hilbert plane. We're going to let AB be the diameter of some circle, so we'll have this circle. And we're going to look at the triangle ABC. So AB is one of the sides of this triangle, and the third point C is on the circle. So this is somebody who's inscribed in a semicircle. And we'll have a picture here in just a second. What we want to do is we want to show that our angle C is right, acute, or obtuse. So 3 options there for our angles. According to whether our geometry is semi-Euclidean, semi-hyperbolic, or semi-elliptic. If it's Euclidean, it's right angle. Hyperbolic, angle C is acute, and elliptic, angle C is obtuse, is how that's read. So respectively should have been added to the end of that sentence. So here's the picture, and this illustration right here is totally in the semi-Euclidean situation because I used a compass and a straight edge to draw it. So here, very, very faintly, you can see the pencil drawing of the circle, and then I went ahead and put in the center O and the diameter AB right there. Arbitrarily picked a point C on the circle and just connected in to form the triangle. And I'm going to go ahead and assume that we know the center of the circle is O. If you weren't actually getting that, technically there'd be a first step where you bisect the diameter AB to get your center. So here's the things that you know for sure, and this is something that we can do regardless of whether we're in the Euclidean or non-Euclidean cases. So in any Hilbert plane, first step you'd want to do is draw in the extra radius of center of the circle to point C. Now, that gives you a radius, so that means that the radius OA, OB, and OC are all going to be congruent to each other because, hey, that's the definition of a radius. Okay. Now, once you have this internal line in the big triangle, notice what that's automatically doing. That means that we're cutting our big triangle up into 2 smaller triangles. Now, any guesses what type of triangles those 2 smaller triangles are? Your choices are equilateral, isosceles, scalene, right, acute, or obtuse. What do you guys think? What type of triangle do we get? For our triangles there are the triangles AOC and BOC. Yep, they would totally be isosceles. They'd be isosceles because in each of these triangles, whether you're looking at AOC or BOC, notice they're formed with 2 radii. So that means you have 2 congruent sides. They're totally going to be isosceles. Now, once you have your 2 isosceles triangles, what's something you know for sure about an isosceles triangle? So let's say we are picking on triangle AOC right over here. What would we know about an isosceles triangle? something automatic. Well, that's the definition. In our case, we found that we first had two congruent sides, then we were isosceles, so there's one extra piece that we're going to get for free once we know it's isosceles. Or now that we know it's isosceles, I guess I should say. So you know in isosceles triangles that the two base angles are always congruent to each other. So here we just found that we have two isosceles triangles. So what we're going to get is two pairs of congruent angles. So we have in triangle BOC, so over here on the right, the two base angles would actually be on the right side and up and at the top. So angle B and angle BCO are both going to be congruent to each other, marked with that single line or single arc. In the other triangle AOC right here, you're going to get that angle A is congruent to angle ACO. Those are your two base angles, which are really on the left and the top. And so that's super duper helpful. And the reason for that is once we start looking at the degrees. So suppose we go ahead and label alpha here to be the measure of angle A or the degrees of angle A. Well, we know A and the left side of angle C up here are congruent. That means the measure of angle ACO is also alpha. I did not write that down, but that would be down here as well. And over here, we've got the angle B. We're going to have the measure of angle B to be B degrees. And we already know angle B is congruent to BCO. So that means the measure of BCO is also beta. Excuse me. Now, let's tie this into C. So we're going to go ahead and find the measure of angle C. But first we see that the measure of angle C is exactly the same as OCA and OCB. Well, we know that those two guys are congruent to these two guys who could totally sub out here for angle A and angle B. And with that skipped step that should be there, the measure of angle C would simply be alpha plus beta. A little bit of a skip step, but not much. Now, that's it in terms of everything that we can do in a general Hilbert plane. After this, we're going to have to get specific. So in the original setup of the question, we were looking at that angle C up there at the top could be right, acute, or obtuse, depending on whether we were in a Euclidean, hyperbolic, or elliptic plane. So I'm going to look at one case because we're close to the end of time here. So we've done this example before when we were in classical geometry, which would correspond to the Euclidean case. The only difference is you wouldn't have used the incidence axiom here. You would have used a postulate from Euclid, and that would be the only difference. Okay? So instead, I'm going to pick one of the non-Euclidean geometries, and because the picture in the last example was an elliptic picture, I'll go ahead and do the situation here of the hyperbolic case. So case one, what happens if we are in a semi-hyperbolic plane? Now, the key thing to remember with a semi-hyperbolic plane is when you sum up all the measures of the interior angles, it's going to sum to less than 180 degrees, and that's the key feature here. That's actually the defining feature of semi-hyperbolic, or just hyperbolic if you prefer. But technically, it's semi-hyperbolic. So if we look at our original triangle ABC, well, what do we know? The interior angles all sum up to less than 180 because we're in a hyperbolic geometry. So you can literally just say, hey, measure of angle A, measure of angle B, measure of angle C. But what did we just find was true in any Hilbert plane? We actually went and tagged an expression for each of those degrees. So we said that, hey, measure of angle alpha was measure of angle A was represented by alpha, measure of angle B represented by beta, and we figured out algebraically that measure of angle C was the same as the sum of alpha plus beta. Well, notice in that expression, you have more than one copy of alphas and betas, so we add them together, and we'll get 2 alpha plus 2 beta, still less than 180 degrees. Well, you factor out the 2, you divide by 2 on both sides, and you'll get the sum of alpha plus beta still has to be less than 90, divide both sides by 2. Well, at this stage, we've just been doing some arithmetic with real numbers. Okay? We now need to pull this back to the geometry. we found way back at the very top up here that alpha plus beta was the same as the measure of angle C. So throw this back into the angles. This tells us that the measure of angle C is less than 90 degrees. That's a definition. Anybody remember what type of angle has a measurement or degrees of less than 90? Your only options are right, acute, or obtuse. No guess? Right, obtuse, acute. I said that in a different order this time. Did not mean to do that. Angle C, what type of angle is it? You know its degrees are less than 90. Yes, there you go. Key thing for this proof. If you don't know the definition of acute, right, or obtuse in terms of their degrees, you are not going to be able to get through this particular example. So this would tell you that your angle C has to be an acute angle, and if we went back to the statement of the question, what we would see is semi-hyperbolic was supposed to give us an acute angle. Bam, we did it. Now, we definitely don't have time for the other two cases, but remind ourselves what they actually are. So up here is the key thing, the sum of the angles. So case 2, maybe case 2 is Euclidean. Euclidean, the sum of your angles has to equal 180. Any guesses what the difference will be in all of this work? If the only thing in terms of the definition that changed or the defining feature that changed was an equals instead of an inequality there? Any guesses how that would propagate through? Don't overthink it. All the inequalities would change to equals. Now, if you get the measure of angle C equals 90, it's no longer an acute angle, and equals 90 is going to give you a right angle. Any guesses what happens with the elliptic? That's elliptic is when your sum of angles is bigger than 180. Anybody got a guess for the elliptic case? Don't overthink it. If the inequality here flips for your defining feature, the inequality flips, the inequality flips, the inequality flips, the inequality flips, and you'll get that the measure of angle C is bigger than 90 degrees. Well, if your measure is bigger than 90, this tells you that the actual angle is obtuse, and that's how you would deal with this guy. Notice each of the three cases are almost identical. The only difference is the symbol that we start off with between the sum of all your angles and 180 degrees, and that's going to give you the difference in terms of your result down here as well of whether you're acute, right, or obtuse. Okay? But that's it. That's the end of that example. I mean, even if we had extra time, I probably wouldn't write out those extra two guys because they're literally identical with just the inequalities changing. Okay? But that's it. That is a snapshot, a very baby snapshot of what can happen in non-Euclidean stuff. But that is it for today. If you guys got any questions, I'll hang out for a little bit, but I don't have anything else for us.